If you could, coming to the second lecture, I see there are still quite a few people I did not scare off first time. We'll see in a few weeks' time how many of you will be still here. What we did last time, let us remind us quickly. Right, I discussed random variables, and from your point of view, a random variable is a result of an experiment. If you repeat the experiment again, you will get a slightly different value. So it's random to some extent. And random variables are linked to probability distributions, which basically they tell you how random variables are distributed. And there are two types, discrete and continuous probability distributions. And I showed you three sort of a very important major probability distributions: Gaussian or normal distribution. I can't see the entire screen, that's weird. Well, we'll see. It's quite common in nature. And what I want you to remember, that 95% of probabilities within mean plus minus 1.96 times standard deviation. I will come back to this number later. Poisson distribution or count distribution, which required random and independent events. Mean equals variance. That's the thing I want you to remember about this. And this distribution approximates Gaussian for large n. And finally, binomial distribution. It's a probability of k successes in n trials. The simplest example is when you toss a coin several times. The probability of having, in this case, that number of heads in 8 throws looks this way. And again, this distribution approximates Gaussian for large n. So today, let's start with a little example. Imagine you weigh a mouse. You take it, put it on digital scales, and you read a number, 18.21. It depends on accuracy and precision of your scales, but that will be a number, and there will be some so-called reading error or readout error linked to this measurement. Or you can try to improve your result. You take 5 mice, you find their mean weight, so you weigh each of them, you find mean weight, you will get another number, but this number will have, you take a sample of mice, so this number will have an error which is called sampling error. So these two things, they are two examples of random measurement errors, and that's what I'm going to talk in the first part of today's lecture. We start with a quote from Ernest Rutherford: "If your experiment needs statistics, you ought to have done a better experiment." So take it to heart. Ernest Rutherford was a physicist, father of nuclear physics. Well, one of the things he did, he formulated for the first time the law of radioactive decay and half-life time. There are lots of anecdotes about him. One of them is that once Rutherford went to his lab late in the evening and he found one of his students working there. So he asked him, "Oh, you're working late in the evenings?" "Yes, yes, I do." "So do you also work in the mornings?" "Yes, yes, I do." "But when do you think?" Silence. There are, generally speaking, two types of errors or uncertainties in measurements. One type, systematic errors, which basically, it's illustrated in this kind of a rough diagram, where in the center of this target you have the ideal value, the true unknown value you are trying to measure, and you have several measurements. So systematic errors will shift the entire group of measurements out of your ideal position, while random errors will create a scatter of these points. And systematic errors are usually either incorrect due to incorrect instrument calibration, some model uncertainties, a change in experimental conditions. If you have to set your temperature to a given value and you change it, you might have a shift in your results, or just simple mistakes. These errors can be eliminated in good experiments, in good experimental practice. You just follow your protocol well. So I'm not going to talk about this anymore. I will concentrate on random errors, which would be reading, sampling, counting errors. I will discuss this in a moment. They could be also due to background noise or intrinsic variability of your subject, and some sensitivity limits where you can't measure things exactly. Now, you can't eliminate random errors. They are there. That's it. So you have to learn to live with them. The best thing you can do is you can estimate random error, and you can actually reduce it a little bit by taking multiple measurements, by doing replicates. And okay, let's go through a little example which I hope will explain you a little bit where measurement errors come from. So imagine you want to determine the strength of oxalic acid in a sample, and you can do it by there are probably lots of chemists here that know much better than me how to do this. Find the volume of sodium hydroxide solution required to neutralize a given volume of the acid by observing a pH indicator like phenolphthalein. And there will be lots, it's a long process, it involves several steps. So there will be errors, uncertainties related to each step of this measurement. So first of all, volume of the acid sample, you have to measure it, so there will be some uncertainty. There is judgment at which point acid is neutralized, that's your judgment, you look at color of the indicator, volume of sodium hydroxide solution needed at this point, and accuracy of concentration of NaOH, which includes both weight of solid compound and volume of water added. Several steps, several uncertainties, they will all add up and they'll create some sort of a random error, so your final result will be a random number. And you can build a quite simple mathematical model of these errors, measurement errors, to understand how they are distributed. And one of them, that's probably the simplest one, was introduced by Laplace, Pierre-Simon Laplace, French mathematician, in 1783, so it's a very old concept. So you can consider a measurement of a certain quantity, and it's unknown, and its true value is, let's call it m0, but we don't know it exactly. And it's in the middle of this graph, so there will be a deviation from this ideal value. And each measurement is perturbed by a certain amount of uncertainties, as I showed you in the previous example. And each of them will contribute a small random deviation, plus or minus epsilon. And in this very simple model, all these epsilons, they have the same magnitude. It's just one of them will increase the result, and another one will decrease. And what happens is here, you start with the original value, you do your first step of your experiment, and you might add uncertainty, plus or minus epsilon. Let's say that they are with equal probability, 1/2. So after the first contribution from all these errors, you are either here or there. After the second contribution, well, if you are here, you have half and half probability going here or there. So probability of being here is 1/2 times 1/2 is 1/4, and the same is in this place. However, in the middle, you can get here by two independent paths. So you have a 1/4 of probability of going here and there, and 1/4 here. So these two add up, and the probability of being here is 1/2, and so on and so forth. It builds a sort of a tree of probabilities, and at the end, the lowest probabilities are at the edges, and the highest probability is in the middle. Now, what does it remind you of? What sort of distribution is it? Well, it will be Gaussian at the end, but I discussed this last time. You remember the experiment? If you toss a coin, yeah, exactly. So if you toss a coin, you have probability 1/2 to go either heads or tails. If you toss it again, and again. So probability of having 4 heads is 1/16, but probability of having just 2 or 3 heads will be much higher. And that leads to a binomial distribution, which for this particular case looks this way. And, and of course, if you have large n, as I told you before, it will approximate Gaussian. So in real life, there's lots of these little perturbations to your measurement. So what you get at the end, the final result is a random variable with something which is roughly a Gaussian or normal distributed distribution. So you expect random measurement errors to be normally distributed just from this simple model. You can demonstrate how it works in practice by a simple mechanical device, which is called Galton board, and it consists with lots of pins, and you drop little balls from the top, and at each pin, a ball can go either to the left or to the right with equal probability. So majority of balls will go left and right, and they will end up down there, but some of them will go very far to the left, some of them will go very far to the right, and what you get at the end is this approximated binomial or even Gaussian distribution. So you can think of this, each ball represents one particular measurement. And you do them many, many, many times. And if you build a distribution of your final results, it will resemble binomial distribution. Another thing I have to mention is biological variability as opposed to technical variability. The distinction between these two is not that obvious sometimes, but for the purpose of this talk, I would just keep it simple. Technical variability is basically what I mentioned, random measurement errors, accumulation of errors, and that will create your measurement error. But on top of this, well, there is lots of biological variability. You are aware of this, especially at molecular level, where there is lots of interactions, basically Brownian movements. Everything is very random, very stochastic. But if you propagate it to higher level, of course, it will lead to phenotype variability. So subject to subject, you have different numbers, different values. If I measure, for example, height of each of you, I will get different numbers. So you are all different. Variability in time, that's another thing. If you measure your, for example, in situ gene expression in a cell, you will notice that it comes and goes in bursts and pulses. So depending on when exactly in time you do your measurement, you will get a different value. So generally, life is stochastic and introduces a lot of biological variability. And in typical experiments, this will be a dominating factor. You'll be dominated by biological variability. And then it's actually very difficult to disentangle these two types. So the only thing you can actually do is to do your experiment in replicates and try to estimate it. Okay, so if you repeat your measurements, what you get will be a sample of numbers. And from this you can find mean and you can find some variability scale. And well, let's have a look at these numbers. So imagine you do an experiment, you're weighing your mouse again, you have 5 of them, you do 5 measurements and you find a mean. So this number is probably an improvement over these 5 numbers, but if you do it again, you will get a slightly different number. If you do it again, you will get again a slightly different number. That's because your sample, it introduces error on its own. It just depends on how you select your sample. Every time it will be different. So this is called sampling error. And it strongly depends on sample size. So especially for small samples, sampling error is very large. I will come back to this later in the next 2 weeks' time. We'll talk quite a lot about this. Now, there are 2 types of errors which are quite easy or relatively easy to estimate without the need of any replicates. You can just have one measurement and say something about this error. So one of them is just reading error. It's trivial, basically, but you have to take this into account. So when you do one simple measurement using something with a scale, like a ruler or micrometer or voltmeter, thermometer, a measuring cylinder, I think this is something you use quite often, or a stopwatch, you will have an error on top of this. So typically this error is half of the smallest division, plus minus half of the smallest division. So if you measure a number using a ruler, it can give you a reading, for example, 23 millimeters, and error would be plus minus 0.5. That's a typical convention here. Digital instruments can give you a readout, which gives you lots of numbers, but not all of them are important sometimes. This is actually a device which I own at home. It's an energy meter. And it gives you actual power consumption at a given moment. So this is 628 watts. And it gives it down, the number is displayed down to 1 watt. But I discovered that it goes up and down in increments of 15 watts. And what's the calibration of this device, how accurate it actually is, nobody knows because it's not given in a booklet. Of course, this is not a laboratory device. A proper laboratory device would come with instruction manuals, so read it and read about calibration and accuracy of the device, because the readout might tell you something not quite what you want to know. Unfortunately, reading error does not take into account biological variability, so if you want to assess this, you will need replicates again. And another error which is quite easy to establish is counting error, and it comes from Poisson distribution, which we discussed a week ago. So come back to our example with dilution plating of bacteria. You have a plate and you have 17, if you count it, there are 17 colonies here. So this count, we can estimate error on this particular count coming back to Poisson distribution, where if you remember, standard deviation equals square root of the mean, which means if this number 17 is some sort of an estimation of the mean, then we can use square root of this as some sort of estimation of the error. And you can do this, and you can find square root of 17, it will be 4. So you can say that this count is 17 plus minus 4. This is a rough estimate of counting error. There are better ways of doing this. I will come back to this later, but that's the simplest example. Let's try to understand it better, what this error really means. Okay, let's do a Gedanken experiment. German-speaking people, what does it mean? Thought experiment. Yes, it's a thought experiment. This is a term used by physicists quite often. It was introduced by Ørsted, a Danish physicist, in 19th century, quite a while ago. And well, famously, it's been used by Einstein many times. He devised these thought experiments about trains going at speed very close to light speed. So there is an experiment, something that you can't really do, but you can theorize about it. So imagine we have a population, we have a distribution of counts with a true mean count of 11 counts. This is something you normally don't know, but you can simulate it. And imagine that you can now measure counts on 10,000 simulated plates, and it's demonstrated here. So for each plate, we found count, Ci, and its error, square root of this. And it's demonstrated here. This is our 17 here, and this is plus minus 4, so this is the error that we estimated. And you start, so this is the first plate, second, and so on and so on. So in the first plate, we had a number 11, then it was 8, and it gives you slightly different result every time. So you can collect all these counts, lots of them, 10,000 of them, and build a frequency distribution telling you how probable or how likely it is to find any of these counts. And you will find a distribution which is basically a Poisson distribution. And what I plotted here is the probability distribution plus its mean plus minus sigma. So it's this theoretical thing, 11 plus minus square root of 11. And if you look at our numbers, this number is exactly the same as the mean because we are lucky. But even if our count, actual count from an experiment, if it is smaller or larger, the error, the square root of this number, is actually quite similar to the actual standard deviation of this distribution. So what happens here, and this is a sort of a reasoning I will repeat a few times later. You perform your thought experiment hundreds and hundreds or tens of thousands of times, build a distribution, and then compare your estimators with the true values. What happens here at each CI, each number from every plate is an estimator of the original of the true mean, while each error, each square root like this, is an estimator of this sigma. So this is the best you can do, and sometimes we are a bit off. For example, this measurement, 17 as opposed to 11, and this error is of course larger than the true error, but that just happens. That's the best we can do, estimate. All right, let's do a little exercise. I will do it with you step by step, so you don't have to do much calculation. So there was an article in the Courier in October 2013 with a big headline, "Dundee is murder capital of Scotland." Quite scary. And in the paper they quoted these data, showing number of murders, and this was, I think, from September to September 2012, 2013. How many murders happened in every of the 4 cities here, and what's the rate per 100,000 inhabitants? So there are 6 murders in Dundee and 19 in Glasgow, but the rate per 100,000 is 4.1 in Dundee and only 3.2 in Glasgow. So they looked at this and they said, yes, we are the worst, so murder capital. Now, let us now compare Dundee and Glasgow. Let's ignore these two for a moment. And let's try to find error bars on these murder rates and just see how large they are. So anytime you do this, if you have any transform counts, if you do something like dilution plating, and you have 17 counts, and then you say that in your original sample you had 17 times 10 to the 5 bacteria because you did a 10 to the 5 dilution. You always have to find errors by taking a square root of original raw counts. This is what you counted by hand, 1, 2, 3, 4, 5, and so on, not on the transformed number. So we have to find errors on these two numbers. Those of you who have smartphones, calculators, whatever, you can quickly check. Error on 6 will be square root of 6, which is about 2.4. Error on 19 is the square root of 19, which is about 4.4. Now we need to transform these errors to these numbers. That will be the topic of the last lecture, how to propagate errors. But I can quickly tell you, if you scale your number, multiply it by a constant, your error scales in the same way. So fractional errors are conserved. Fractional error on this will be exactly the same as fractional error on this number. So fractional error on the first number, on Dundee number, would be this, 2.4 divided by 6, which is 0.41. And for Glasgow, 0.22. Now, have a look at this number. It's 41%, so fractional error on this number, 41%, is a huge error. It's just because we are talking about small numbers. So every time in statistics when you have small numbers, especially counts, your errors are going to be huge. And now you can apply these numbers, basically multiply this by this to murder rates, and they will be like this, 1.7 and 0.74. Graphically presenting this, well, you can see that error on Glasgow murder rate per 100,000 population sits entirely within this error. And if you do a proper test, in this case, chi-square test, it will give you a p-value of 0.8, which means that there is absolutely no statistically significant difference between these two numbers. I don't expect journalists to understand this, but you should understand it. If you look at all numbers, I did it for you here, so only Edinburgh seems to stand out with a much smaller p-value here, but all these three cities have basically comparable error, murder rate. This is all within error bars just because there are all small numbers. So to summarize the first part of this talk, experimental random errors are expected to be normally distributed. Try to remember this, it's quite an important thing. Some of these errors can be estimated very quickly in a simple way, directly, like reading error and counting error. And for other uncertainties, you need replicates. You need a sample of replicates, and then you can do your other estimates. But this on its own introduces sampling error, and we have to deal with it. Okay, the second part of the talk, I will begin with another example, or actually it's the same example of measuring our 5 mice. So if you have these 5 numbers, you can actually calculate, apart from the mean, you can calculate many other things. You can calculate median, standard deviation, standard error, and probably a dozen of other things. All these numbers are called statistical estimators. And this is the topic of the second part of the talk. This is the quote from Des McHale. You probably don't know him. He's a mathematician. He's a professor of mathematics at the University of Cork in Ireland. And apparently he's a very funny man. So he compiled, one of the things he did, he compiled a list of answers to, questions to talks which you don't understand. So if you go to a seminar talk or a conference talk, and at the end, the chair asks, okay, are there any questions? And there is an embarrassing silence because nobody understood anything. One of the questions he suggested, you might get up and say, excuse me, which textbook would you suggest for someone who wishes to get his students involved in this area? Useful? Yes, only PIs understand this, really. Population and sample, before we get to statistical estimators, I have to quickly discuss this. So this is a term which is nicked from social sciences, and it's been around for many years, but it is used now generally in statistics. So the meaning is a little bit different. So population is, of course, lots of, for example, people, and then you select a sample of a few of them. Who are they, by the way? Can you recognize these people? Watson and Crick. This one? Okay, we'll come back to him. This is Ronald Fisher, one of the greatest statisticians of the 20th century. I don't know this guy. Most biological experiments involve a sample selection, but as I said, these terms, population and sample, are not as literal as here. So what is a sample? Unfortunately, sample has different meanings in biology and statistics, so we have to explain it to avoid confusion. In biology, sample is a specimen, so you take something, this is your sample. A cell culture or something like this you want to analyze. And if you do an experiment with 5 replicates, you will have 5 specimens. You would call it 5 samples. However, in statistics, the meaning is slightly different. So if you do quantification, for example, mass spectrometry, and find, I don't know, abundance of a particular protein or peptide, what you get at the end will be 5 numbers. And from the statistics point of view, this is our sample. So sample is just a set of numbers or measurements taken from a larger population. And in these talks, I will usually denote it as x1, x2, up to xn. So biological sample is not the same as statistical sample. This is what you get from your experiment, set of numbers, while population can be somehow an abstract concept. It's huge in size, usually impossible to handle, while well, that's the advantage of a sample. It's easy to handle. It's just n measurements. So if you have 12 mice in a particular experiment, that's your sample. The population will be, I don't know, all mice on Earth, all mice in the country. It's a bit vague. The same, if you have 26 patients with eczema, then it will be all people with eczema. Or if you want to compare it to general population, then it will be all people. If you have 5 biological replicates where you measure gene expression, and for one particular gene you will have 5 numbers, the population here is all possible measurements of this particular gene expression, which is an infinite population. This is only a hypothetical thing. This is not a real population. But you still can sample from this. You can take a sample and do your measurements. So population is a subset of a sample is the subset of a population. And while population is described by unknown parameters, this is a parameter like mean, standard deviation, and so on, the sample of size n is characterized by known statistics or statistical estimators. So this is this term, statistical estimator. Sometimes you use a term statistic, it's a singular, and it describes sample parameters. So one statistical estimator approximates the corresponding parameter in the population. So sample mean would approximate population mean, sample standard deviation would approximate some population standard deviation. Now, let's go back for a second to our previous example. If you have dilution plating experiment, you have 17 colonies. Now you tell me, what is the sample size here? 1? Who thinks differently? Silence, you don't think. You should. Everybody agrees it's 1? Yes, it's 1. That's true. Some people might say it's 17 because there are 17 colonies here, but no. This is one measurement, and this is measurement, you can call it x1, the first measurement, it's 17. Again, I told you about this experiment. If you do many plates, you take 3 plates, for example, your sample size will be 3 because you've got 3 numbers. So this is the correct answer. Let's go back in time. This is a fragment and a nice picture from a very old book called Geometry by Jakob Kobel, which was published in Frankfurt in 1575, so it's over 400 years ago. And a particular fragment related to this picture says, "Stand at the door of a church on a Sunday and bid 16 men to stop, tall ones and small ones, as they happen to pass out when the service is finished. Then make them put their left feet one behind the other, as illustrated, and the length thus obtained shall be a right and lawful rood." Rood is a unit of measure which is 16 feet. "To measure and survey the land with, and the 16th part of it shall be the right and lawful food." This is actually quite remarkable. 400 years ago, Kobel introduced random sampling from a population. Even more, he required a representative sample. He said clearly, man, tall ones and small ones, just select randomly people of different sizes, because presumably they have feet of different sizes. He defined standardized units of measure, root and foot, to measure land, and used 16 replicates to minimize random error. This was quite clever. And he calculated a statistical estimator, the sample mean, over 400 years ago. Of course, he didn't know these concepts, but at least the idea was very good. As I said, statistical estimator is a sample attribute which is used to estimate a population parameter. This example shows a population, normal population. You remember this notation. This is a normal distribution. The mean is 20, the standard deviation is 5. So that will be our mice, let's say, weight of a mouse. And this is a sample which is represented here by individual dots. This is the histogram of the sample, and it kind of approximates the population. In the same way as mean, sample mean approximates population mean, and sample standard deviation approximates population standard deviation. You can calculate these things and write it down. There are a few things you can calculate apart from mean and standard deviation, mean, median, proportion, correlation, and so on. I will explain some of them later. But let's have a look at standard deviation first. It's there is more to it than you might realize. So very generally speaking, standard deviation is a measure of spread of data points. So you can have a general idea how to find it. So you can calculate the mean of a sample. This is our sample of 12 measurements, and each value is plotted here as a blue dot. This is the sample mean. Then you can find deviations from the mean for each point, and they are represented by these bars. Now you see that some of them are positive here, and some of these things are negative. So if you add them together simply, they will mostly cancel each other, and you will get something which is very close to 0. So you have to get rid of negative signs, and then you can combine them together and hope it works. Surprisingly, you can do it in many ways. There is more than one way of doing this. You can get rid of negative signs by taking a square of this number. So this is the sample point, x1, x2, and so on, minus mean squared. Then you calculate the mean and square root of this. And this is a sort of standard deviation. You are probably more used to this form, where you don't calculate the mean, but you divide it by n minus 1. The reasons for this are a little bit complicated. I just mentioned that it is that this squared is an unbiased estimator of variance, which means it represents the true variance much better than this one. So this is a little bit better than this one, and in most cases you are going to use this standard deviation form. However, you can follow this prescription here in a different way. So you can get rid of negative signs by just using absolute value and then simply calculate the mean. So this is called mean deviation, and it's a different way of estimating spread of your numbers. There are some problems with it and some advantages as well. So for example, it doesn't overestimate outliers. Just because there is a square here, points that are far away from the mean will contribute very strongly to the standard form of standard deviation. They won't affect this that much. However, this form, mean deviation, is less accurate than standard deviation. It doesn't represent the true population value that well. And also mathematically, it's more complicated. It looks simpler, but actually calculating derivatives is a problem, because derivative of the absolute value is discontinuous. And basically tradition. Standard deviation has been around for donkey's years. Everybody uses it. So it's basically, this is a forgotten thing, but there are still some people who try to use it. So don't be surprised if you see it somewhere. Now I want to spend some time explaining the standard error of the mean. I'm sure each of you has calculated standard error at least once for various reasons. But what the meaning of a standard error is a little bit tricky, so I'll try to explain you. Let's do our Gedanken experiment again. So consider a population of mice with normally distributed body weight. The mean is 20 grams, the standard deviation is 5 grams. And now we take a sample of 5 mice, we weigh them, and we calculate sample mean for this one. So we have mean weight of 5 mice. And then we do it again and again and again, like in the example with Poisson distribution. So these are our samples. The first sample, you see these gray dots here, that represents actual measurements. This is the mean plus minus standard deviation. The second measurement is slightly higher, and so on and so on. Sample number 5 is interesting because it's very tight. All numbers are very close to each other. That one has much higher standard deviation. So both mean and standard deviation change from sample to sample, as you expect. You take over means, you take 10,000 of these, and you build a frequency distribution of these means, distribution of sample means. Okay, that's fine. And presumably you can think of this because the means are distributed like this, then the width of this distribution perhaps could be some sort of an estimator of how accurate our mean is. Interesting thing happens when you change the size of your sample. This is the sample of size 5. If you use 30 mice instead, you see the means are much tighter, concentrated around the true mean of 20. And this distribution, the distribution of sample means, is much narrower. 5, 30, 5, 30. So with bigger sample, with more replicates, you can measure things much more accurately. And we can use this. This is called sampling distribution of the mean. This is a technical term I'm going to use a few times in future. So as I said, the larger the sample, the narrower this distribution. And you can show mathematically, there is a proof for this, that the standard, first of all, this distribution is Gaussian by itself, regardless of the shape of the original distribution. And the width, the standard deviation of this distribution, is the original standard deviation of your population divided by the square root of n. We try to use this, but we can't calculate this because we don't know sigma. Sigma is a population parameter, it's unknown. So the standard trick in statistics, if you do calculations on population parameters, you replace them with corresponding estimators, and what you get is also an estimator. So I replace sigma by the standard deviation from a one particular sample and get standard error. So this standard error estimates the width of the sampling distribution. This is the meaning of this. This is the width of the standard distribution. You can have a look at this again. This is the same picture for 5, n of 5, and this is for n of 30. And now I added, apart from the mean and standard deviation, I added standard error. So standard error for each sample is, of course, different. It tries to approximate this ideal number here, which is not known. So if you are lucky, like here, you get a standard error which is very similar to this, but you might be unlucky and you get much smaller standard error, which is probably about half of this value. So every time you have your sample, have your replicates, and you calculate standard error, yes, it is the error of the mean, but technically speaking, it's only an estimator of the error of the mean. So there is also uncertainty in the error. There is error in the error. Keep that in mind. This is a simple comparison between standard deviation and standard error. You probably know this already. Standard deviation measure is a measure of dispersion in the sample, while standard error is error of the mean. This one estimates the true standard deviation in the population, unknown one, and this estimates the width of the distribution of sample means, the sampling distribution. Standard deviation does not depend on the sample size. As you can see, these standard deviations, they are sometimes smaller, sometimes larger, but roughly the same size for 5 and for n of 30, while standard error gets much smaller here. So the larger the sample, the smaller is the standard error. And the last thing for today, a quick explanation of, it's yet another estimator, correlation coefficient. You are familiar with this, of course. You have pairs of points this time. So a sample, well, you can either think of this as two samples of the same size or one sample of pairs, x1, y1, x2, y2, and so on. And you calculate correlation coefficient. When data are correlated or anti-correlated, it's close to 1. When they are not correlated, it's 0. This is the actual formula. It might look a bit scary, but let me try to explain it because it's actually very simple to understand. So you have a sum of these things, and each of them, look at this. This is something you probably know as a z-score. It tells you how far a given point is away from the mean in terms of standard deviations. How many standard deviations you are away from the mean. So you can call it zxi and zyi. So there is basically a sum of these products of z-scores. By the way, correlation does not mean causation. This is this famous example where in Australia, when sales of ice cream go up, shark attacks also go up. It doesn't mean that ice cream causes shark attacks. So if you see in biology things that are correlated, don't conclude that one causes another. It's not that easy. Right, let's come back to our formula. It's plotted here. So it's a product, sum of the products of these two things. If you have a sample of 6 points which are highly correlated, this is x, this is y, the correlation coefficient is 0.99. This is the mean x, and this is the mean y. So our z-scores are how far you are away from the mean in terms of standard deviation. Let's have a look. The first point here is to the left of the mean and is below mean in y and x. So you have a negative number here, negative number there. You multiply them, you get a positive number. And so on. These are always negative both in x and y, and these are always positive both in x and y, because these two things are correlated. So you have, in this sum, there is a sum of positive numbers, which will give you a high number. While if your points are randomly distributed and correlation is low, this point, for example, is the first point here. It's to the left of the mean in x, but in y, it's above its mean here. So you have negative number, positive number, the product will be negative. Another one is positive, negative. So there is a randomness here, and you have a sum of randomly positive, negative numbers, and this sum is going to be small. Statistical estimators, just to summarize them, there is many more. So to express the central point of your data, we discussed the mean. You can have geometric mean, arithmetic mean, you can have harmonic mean. There are various flavors of the mean. You can calculate the median, mode, which is the peak of a distribution, where they peak. You can calculate trimmed mean by rejecting outliers, which is a bit dodgy, but sometimes people do this. To estimate dispersion, variance, standard deviation, mean deviation, this is what I showed you. You can calculate range from the smallest to the largest point, interquartile range from, let's say, 24th to 75th percentile. That would tell you something more about your data, or even mean difference between every pair of points in your data. And there are many more. You can estimate symmetry of your data, skewness, kurtosis, how symmetric the shape of a distribution, and dependence for pairs of data, or even more multiple data sets, correlation or distance, various types of distances. That's just a small selection of possible estimators. Each of them estimates something general, something unknown in the population. Okay, that's it for today. Just to remind you that the slide handouts are in a different place than before. Thank you.